Here's a quick look where we're going today, an introduction, what simulation is, definition will be on the very next slide, and what it can accomplish and how it can help the bottom line. And we'll mention several case studies, 2 or 3 out of dozens and dozens. You can't see it over the internet, but I'm old and wrinkled and gray. I've been doing simulation a little more than 35 years, and that's almost exactly half my lifetime. So what is simulation? Well, it's not a rabbit that's going to come out of this hat. There's a definition of it. Now, what's so appealing about this particular thing called simulation? Well, you can experiment with the model, and that's a lot cheaper and less risky and quicker and less disruptive than experimenting with the real system. Now, a very dramatic example of that would be a new model proposed for a ship. Well, you'd rather say the model isn't going to work the first time and needs refinement. You'd rather sink the model ship in the bathtub than sink the real one in the ocean because you didn't model it beforehand. So hold that thought as we look at some of these nice things simulation can do. Simulation, as I'm speaking of it today, and it's not the only type of simulation, is called dynamic. That means that the simulations we build here and that I'm accustomed to building through experience are time-driven. There is a conceptual system clock. The system being modeled knows whether it's lunchtime or mid-afternoon or dinner rush or beginning of the morning shift, whatever it might, time dependency might be. And in almost any real system, there's going to be unpredictable variation. Downtimes are hard to predict. Variations in arrival rates of customers, hard to predict. Service times vary, travel times vary. All of this can be incorporated in the model using well-defined statistical and analytical techniques. And as a communication aid, animation and the building of the animation nowadays with the simulation software out the last few years requires, probably at most a 3 to 5% incremental effort over building the model. In fact, some of the newer software we use, going from 2D to 3D animation on the computer screen, whichever is more instructive and informative to look at, they're one mouse click apart. And the animation greatly helps communication. Now, there is one caveat. A fancy animation will not make a wrong model correct. That's worth a whole chapter in a book by itself when you dig deeper into simulation and what it can do for you. Well, meanwhile, looking at the high level of why would one simulate, it's a lot cheaper to make conceptual mistakes during system design on a big sheet of paper or on a computer screen, and the same goes, how should I operate my factory or my warehouse or my restaurant or my airport or my operating room or my hotel check-in service? Well, the list of things I put in that sentence illustrates the broad capabilities of simulation, both for getting the system right in the first place and operating it day to day, week to week, month to month to best advantage. And simulation is also very good at helping reduce costs. You can use it to reduce cycle times, not keep as much inventory on hand, and yet still avoid stockouts, and reduce the amount of material handling. when you reduce the amount of material handling. And this applies particularly to factories, warehouses, container ports, all of which I've simulated. When you reduce material handling, you save time, you save fuel, you save wages, you reduce potential for damage, and on and on. You reduce a lot of things that are very nice to reduce. You can't get rid of them totally, but greatly reduce them before your competitors do. Now, when to simulate? Very important one here, and simulation can help address questions of equipment maintenance policies. For example, a piece of equipment is due for an overhaul after 10,000 hours. At 9,500 hours of use, it breaks down, so it's going to need repair. Is it better to pull the maintenance you were going to do ahead, or get it repaired, run it another 500 hours, and then do the maintenance as regularly scheduled? That question commonly comes up. Simulation can provide an optimum answer to it. Processes exhibit cycle time variability. Well, most processes do. And classically, the way to cover for cycle time variability is to have bigger buffers. Simulation can avoid giving in completely to that temptation. Processes are highly interdependent. Well, nowadays they usually are. The traditional statistical methods in the first semester of statistics typically assume independence, not correlation or interdependence. That's much harder to handle on a sheet of paper with formulas, but quite easy and routine to handle with simulation. You haven't even built the process yet. You want to build it the best way possible. Well, simulation will help you design exactly what you should build. Now, you might have competitive pressure. I've been looking for a client or company that is not under competitive pressure, but I haven't found one yet. I think in order to find one, I'm going to need to buy myself a spaceship and look around on some other planets. But if you folks out there, but still on this planet, have competitive pressure for these things, simulation can help you meet that pressure. And same header. This comes up very often. For example, the first half of this bullet point, you may have semi-automatic machines, by which I mean a worker sets it up, puts the part on, presses a button, the machine cycles automatically. The worker, if you design the process well, can then go off and productively do something else, but not too far away, and then come back to do a tear down, take the part off the machine, check the quality of machining, check the machine, etc. That would certainly be a high degree of worker-machine interface. If you have a lot of forklifts or tugger trains moving around, worker material handling equipment likewise becomes very important. The same thing also applies in the particular case of bridge cranes. Another mention of that will come up later. And possibilities for resource shortage and blockage. Well, AGVs can very easily get blocked if you don't design the routes carefully. You can always avoid resource shortage by buying a whole warehouse full of resources. Well, that gets expensive. Simulation will help you avoid resource shortage and yet not overindulge on the level of resources, whether they be employees or machines, whatever they might be. Unpredictable storage requirements. Inventory may be highly volatile, depending, for example, on seasonal trends. Simulation can help meet that challenge in the best possible way. And here again, I've been looking for clients who who rarely need to change their products. Their customers are content to go on buying the same thing year after year, and we don't have this worry about product changes. But I think I'm going to need to get fuel for that rocket ship if I want to find a situation like that. Our clients tell us that they're under frequent, well, just look at cell phones, for example. That's one of the obvious examples frequently in the news. So increased power of simulation. Well, current simulation software has leveraged the fact that hardware gets faster and faster and faster. A big model now will typically run faster on the desktop than even a small model would have run when I started in this field on desktop computers 15 or 20 years ago, much less when I started doing simulation on mainframe computers about 35 years ago. The 3D animation imposes relatively little hardware load, and it imposes relatively little modeling time load. I've mentioned it pretty well comes with the software and requires little additional modeling effort and gives in return a big advantage on communication value. And some of the simulation software tools have a lot of statistical capability built in. You may still need, for more advanced situations, you may still need a back-end statistical software package, or use the one in our office. We've got several, so that shouldn't be a problem. And with much of the simulation software available today, a person can learn about 80% of the modeling power in a relatively short time. By that I might mean 2 or 3 weeks. The remaining 20% would take quite a bit longer. That's why I use the hockey stick metaphor and a little clip art. But the remaining 20% is likely needed for only a small percentage of projects. But there's always an expert around. A particular client of ours may or may not want to invest the time to develop in-house expertise, depending on how much modeling work they visualize doing. So if it's only a little now and then, we can provide the deep level expertise. If it's going to be a lot, you really want to ramp up in your company, we can provide instruction to provide you the expertise in-house. And simulation software is much better now because it's gone from procedural languages to object-oriented languages to make it possible to build libraries like the ones we've got here, in-house libraries, build it once, use it many times. And there's greater flexibility. Simulation software will talk nicely, both on the input end and on the output end, to an Excel spreadsheet, and everybody uses those now, databases such as Access, and process control systems right on the factory floor. And I've mentioned the flexibility of animation. It's possible to tell a big simulation model, well, I want one animation screen to look at Department A, I want another to look at Department B, and I want another to look at Department C, and one mouse click will toggle me among the different animation views, what's going on where. And a lot less keyboarding and a lot more mouse clicks, just pull-down menus, to implement even rather logically complex things in a model, like a particular queuing system priority, for example, that might be partly based on first come, first serve, and partly based on priority level, and so forth. Oh, I mentioned several real-world case studies to come. All three of these are among the dozens I've been involved with over the years. Service industry, scheduling the workforce. Now, this particular service industry was a hospital operating room and recovery room. Indeed, simulation, which historically started in manufacturing, has stormed very aggressively into the healthcare industry. And this particular one was in healthcare. But it could conceptually have applied to a bank, a restaurant, or a hotel. The second bullet point was material handling, the downstream local warehouse or storage area at the end of a production line. And the third one was an actual manufacturing line within the automotive industry. Specifically, that was in a first-tier supplier to what here in Detroit we call the Big Three, a bit chauvinistically perhaps, and this was a supplier that supplies seats and sends them to be assembled into automobiles. So those are several real-world case studies to mention, and we've got many more on our website and available in case of interest on request. Now here's an example, and I could have made this 6 or 8 slides instead of just one, but here's one to get your thinking started. What should be stored where? Ease of drop-off, ease of pickup, reduction of picking time. If the forklift has to go through the warehouse picking up a multitude of different things for one or different orders, in what order should they be picked up? How many forklifts do we need? We've actually helped clients who began with too many. They were getting in each other's way, as well as using unnecessary fuel and labor. And what paths should the AGVs follow? Well, that's best decided early before you put those magnetic strips into the concrete floor. Conveyors, what kind, how wide, how long, at what speed, where should they be put? The harbor, the port, which ship should be unloaded or loaded first? Same in a railroad freight yard, perhaps supplying your mine or your cement making facility. That's one we modeled, cement making. In what order should they unload the freight cars? If they don't unload a freight car promptly, the railroad will charge, you kept it too long. On the other hand, if they unload freight cars in the wrong order to save that relatively small cost, they have to shut the furnace down. Well, it wasn't a furnace, it was called a kiln. That's a big cost. So don't do it that way. Staffing levels. That can be particularly important not only in factories, but in hospitals, clinics, restaurants, hotels, and banks. We've helped all of those with staffing levels. Prioritization of customers, partly to keep your staff productively busy, partly to maintain goodwill as best you can. You'll have to take some customer last, and that customer won't do so well on the goodwill, but you do the best you can. And I promised a second quick mention. The last bullet point is much more specific. Bridge cranes. If you have 2 bridge cranes on the same rails in the same bay, under what conditions should one of them be allowed to shove the other aside in order to fulfill its immediate task? How should that be prioritized? So here are some of the simulation softwares we use, and which one is best? Well, whichever one is best for your particular purposes. That's a question we frequently get asked, and when a new project is pending, well, the best one might be the one you already have or know a little bit about. If not that, the best one is the one best adapted to your project needs. So before we pick one of these, we'll ask you lots and lots of questions about what you need done as a client for maximum benefit. Everyone here at PMC doing simulation is required to know 3 of these, and actually I know 5 of them. I'm one of the older guys. Even I don't know all 12 of them, but we've got expertise on all 12. So there's plenty of good software to choose from, lots of worthy competitors. We're not beholden to any one of them.